Okay, let's get through these. I think there are 5 of them. So the first one is for a constant pressure process. Constant pressure is the simplest one. I have a change in volume from V1 to V2. I have a pressure that does not change. And your work is simply the area. In this case, the area is just the area of a rectangle. So it's just pressure times change in volume. Super, super simple. One of my favorites to do. So like last time, I see that my pressure is a constant. Because it's a constant, it comes out of the integral. There's nothing else there, and so I just have my initial pressure times my change in volume. I can also, if I want to, make this in terms of specific volume by bringing the mass out right here. That's the same equation. I just made one specific volume and the other one just regular. Okay, so that's the simplest one we're going to have. The second one is for a constant volume process. Okay, I lied. This is even simpler. Now, we've been talking about how it's pressure times a change in volume. Well, if I have no change in volume, then I have no work. You can't have boundary work if your boundary doesn't change. Remember, that's the whole point here. We have a moving boundary. If the boundary moves, I do work, or work is being done. In this case, no moving boundary. But that's okay. We don't have to have every process producing work. In many cases, we would want to have something like this to help ourselves produce even more power. Like, for example, I could draw a cycle that looks something like this. So I have, I'll make sure I do this right. It's actually going the wrong direction here. So I'm going to redraw this arrow going up. There we go. So I could have expansion at a high pressure. I could have some sort of constant volume compression. Probably be like rejecting heat. And let's see here. Constant volume change in pressure. And then I could have it be compressed at low pressure. This would be my work that I produced. It's a lot, and I use those constant volume processes to do this. In like applied thermo, you'll learn that we typically, if we're having cases like this, we're adding heat at one, and then we're removing heat at another. That's how we actually manage to do that. But we're not there yet, and if you decide to go with a good track of arrow, well, you won't have to worry about that as much. Okay, so constant volume, definitely easier than constant pressure because it's just zero. It's constant volume, it's not doing any work. Next one, isothermal. I'm saying that the temperature stays constant. And as a note, the shape of this line on a PV diagram is actually like set by it being isothermal process. There's actually a little equation for it, which you get later on in the course. For now, you don't really need to worry about drawing these things to scale. Like we never draw this, these lines to scale. Just know it's a slightly curved line, slightly down. And when it's going from one pressure to another and one volume to another, the temperature is a constant. Okay, so in this case, you see that my pressure is changing with volume, which means we have to do an integral. And so that's not super easy. Now, luckily for us, we can bring in our ideal gas law to help us out here. So I've got my ideal gas law. I say, okay, I need to solve for pressure. And so when I do that, I get pressure is equal to this stuff, which is a constant, divided by my volume. And so that's why you see this little C right here. It disappears later on because we don't need it, but it is there for a minute. And then I integrate. And I get this one. How did I get there? You can go ask your calculus teacher for that. Just know that's the nice set equation for us. So I have my pressure initial times my volume initial times the natural log of my change in volume. And that gives me my work for an isothermal process. Okay, polytropic. First off, what in the world is polytropic? I'm going to go ahead and give you just like a heads up that this is eventually leading to isentropic. Isentropic meaning that your change in entropy is equal to 0. Technically, a polytropic process is more general than that, but we're eventually going to go to it being an isentropic process. We'll use this equation to do that. So just know that eventually when we learn about entropy, entropy being that, we lose useful work, this polytropic process is going to become really, really handy. For now, just know it's a very, very general form. In fact, if I change this constant in right here, it can turn into an isothermal, it can turn into various other types of processes. It's a very general form. Okay, so with that being said, and me having said general like 18 times, let's keep going. So first off, in a polytropic process, the pressure times the volume, which is raised to the n, as a note, that's just the volume being raised to the n, not both of them, is a constant the entire time. So I'll put this in my equation, and I can say, okay, I've got this constant right here, and I've got v to the n. Now if you're wondering, why is this v to the negative n here? That's because I solve for the pressure. Pressure is equal to c over v to the n. I could also write that as being equal to c times v to the negative n. Okay, then when I integrate that, I get all of this. Notice the change in exponents. We try to simplify it a little bit, and it comes into being this equation right here. So my initial pressure times volume minus my final pressure times volume minus my initial pressure times volume, all over 1 minus n. N being your constant, and n cannot be 1. If it is, everything goes absolutely bonkers. And what is n? Well, eventually for an isentropic process, we're going to say that n is equal to what's called the ratio of specific heats. Now, you don't need to know what a specific heat is yet because we're not there yet in this chapter, but we will learn about those in this time. But just remember that n is the general form, and it will have a more specific form as we move on. Okay. We can also put this in terms of temperature because we can use our ideal gas law. And it makes it nice and simple there because we know the temperature of the first point and the second point, we can go ahead and calculate it. Okay. There's only 4 of them. I should have counted. So with all of these, you can solve the problems you're going to be running into. It will usually be some combination of these different processes leading to an overall cycle that might produce power or might take power to run. Either way, make sure you write down these equations, and I think I will see you all next time. Bye-bye.